extensive properties in curve system didn't change with the time. So we don't have the items in the left hand side in the linear transport series. So we can reorganize the equation. We only have the items in the right hand side in the linear transport series. So we only have the properties changes in the control volumes with the time and the control service. Integrate all of the property changes along the control service. So if we only focus on the extensive property is the mass, so we know that the intensive property B is equal to the 1. So the continuity equation showing here, we only focus on the mass in the control volume change with the time plus the outflow rate minus the inflow rate along the control surface. So we call that is the continuity equation. And then we have quickly the slide introduce the working equations for the continuity. So the most important thing included in continuity is the flow rate and the velocity and the mass accumulations. These items indicate the mass in the control volume change with the time, so you can identify the items for the mCV is the positive, and we can conclude that this is the accumulations. Okay, and the second I highlight here because I think most important things when we apply the continuity equations, we need to sketch the control volumes and decided where is the control volume, and then you need to depict the control surface boundary. Okay, after you determine the control surface boundary, you actually know where is the inflow and where is the outflow. So you can make the flow rate balance, and then you need to understand the mass changes in the control volume with the time. Okay, and finally you can validate the accumulation system or not. Okay, so we have the table summarized two formulas for the continuity. The first one is based on the integration ideas. So we do the integrations along the control volume and along the control surface. And the bottom here, we just based on the mass flow rate balance will equal to the mass in the control volume is accumulation or not. And the final one is especially for the pipe systems of the continuity equations. As you can see, for this item, we don't have the mCV change with the time. We only have the outflow rate and the inflow rate balance. Okay, so this is a special case for the continuity, especially for the pipe systems. So in the following exercise, we will introduce how to apply the continuity in the pipe flow system. Okay, so last week we very quickly done we have done the exercise, and as the exercise is showing here, you know that we need to define the control surface first, and the inside is our control volumes. Okay, after we decided the control volume, and then we can based on the continuity equation to step by step to identify each items in the continuity equation. For this equation, we only have the information is the alpha rate and infrared, and we need to answer what is the MCV dt. So that's the question showing here is the stored and removed. So you need to decide it. So this is questions, we know that the MCV dt is the positive, so we know that the system is accumulation. Okay. So the second exercise, also we need to apply the continuity to calculate the rate of the water rising in the reservoir. Okay, so the most important thing in here is the rate. So the exercise already depicted the control surface. So the dash line showing here, we already know we have the control surface, and we fix the control surface, and then inside is our control volumes. So this is the conditional is the control surface. So the idea shown here, we know that we have the continuity equation is equal to the dNCV dt and the alpha rate along the control surface minus the infrared along the control surface. So because we fix the control volume in our questions, and we know that the water levels were rising, okay, but we didn't know the rate of the rising water. So the unknown parameter showing here is the V3. We didn't know the V3. So we need to answer how large the V3. And then because we fix the control volumes, so we know that the volumes, the mass inside the control volume didn't change with the time because the white water is rising. So inside the water inside the control volume is always constant, didn't change it. So in that case, we know that we don't have the items for the MCV dt will equal to the 0 because the MCV in control volume didn't change with the time. Okay, so what we only have the sum of the alpha rate along the control surface minus the infrared along control surface will equal to 0. Okay, so how many outflow we have? The cross-section area for the of 2 and 3 are related to the outflow, and the cross-section area for the 1 is associated with the infrared. Okay, so we can calculate the alpha rate for the section 2 and the section 3. So we know that the Q2, we have the Q2 at the section 3. Okay, so we know that the outflow, the mass flow, mass alpha rate along the section 3, the 2 is equal to the density multiply the Q2 is the mass flow rate along the outflow section 2, and the plus at the across section 3 we only have the areas. We only have the area 3, and we don't know the velocity. Okay, and this is also equal to the discharge, and we need to multiply the density to convert to the mass flow rate. And the inflow, so we need to have the minus at the cross section 1, and we still only know the discharge Q1, and then that will equal to the 0. So we just divided the density both sides, so we can cancel out the density. So we can rewrite the equation will equal to the Q2 plus the A3V3 minus the Q1 will equal 0. And our target in here is the how large for the rising rate of is the V3. So we just rearrange the equation. We know that the V3 will equal to the Q1 minus the Q2 divided the A3, right? And so we can write down all of the number we have known. So the Q2, Q1 is equal to the 400 and 000. The unit in here is the CFS. As you can see here is the CFS. So what is the CFS? The CFS is equal to the cubic foot, okay, per second. So similar, when we talk about the CMS, we are equal to the meter cubic per second. Okay, so in here the dimensional is the ft cubic per second minus the discharge Q2 is equal to 250,000 ft cubic per second, and divided the total area is the water surface area is a 14 miles square. 14 miles square. And then we know that the 1 mile will equal to the 5280 ft. So we can convert the mile to the ft for our questions. So it's equal to 5280 the ft per mile. To convert our mile square to the ft square. So we need this is a square, okay? So you can use the calculator to check the answers for these questions. Okay, so I use my calculator to check the answer showing here. So the answers for my calculator in here is the 1.345 and 10 minus 4 powers. The unit in here is the ft per seconds. So we can convert the unit to the ft per hour. So we can multiply the answer by the 3600 seconds. Okay, so that will equal to the 0.484 ft per hour. Okay, so for these questions, because we fix the control surface along the water volumes boundary, so that we especially for this question we already know that the water surface is rising. So we need to require to answer the rate of the rising of the water. So we have the one condition is the mass in the control volume is always the constant for these questions. The next exercise is also apply the continuity equation to predict the time for the tank to drain. Okay, so as you can see, what's our problems? We know that the 10 centimeter jet and from the 1 meter diameter tank. Okay, so we just write down we have the jet diameter is 0.1 meters and the diameter of the tank in here is the 1 meter. And we assume the Bernoulli equation apply. So the velocity in the jet is the squared is the root of the 2gh. So as you remember, the Bernoulli equation tells us that any 2 points along the straight line is satisfy the Bernoulli equations. So we know that the V jet in here is the root of the 2gh. Okay, and the h in here is the water depth. And so how long will it take from the water surface in the tank to drop from the edge? Initial water depth is equal to 2 meters to the edge. F is the final, only have the 2.5 meter. Okay, so as you can see, for this question, we first need to depict the control volumes, define the control volume, and depict the control surface boundary. So we just define our control surface boundary inside the water boundaries. So the yellow line depicted here is our control surface, and the inside is our control volumes. So in these problems, we only have the one outflow in here, and then there is no any inflow. So we go back to write our continuity equation. We know that the mCV dt only have the mass flow rate out, but we don't have the inflow rate. So will equal to 0. So we find out the item step by step. So first, what is our M rate? So as we already have the velocity is V jet, okay, and the diameter in here is the 0.1. So we know that the area for the outflow rate is 2 over pi and dj squared. Okay, this is the area multiplied the velocity is the discharge. So we need to also multiply the density for the M rate. Okay, and what is the mCV? Okay, so we know that the mCV that indicates the water mass inside the water tank. It depends on we have defined the control volume showing here. So we know that the mCV is equal to we know that the tank area is the A, and if we know that the water depth is the H. So this is the water volume inside the tank, and we multiply the rho. Okay, so we have the control volume, the water mass in the control volumes. So we just use the differential, the mCV dt, because the rho and A is the constant values. So we only have the dH dt. Okay, it's the water depth change with the time. Okay, and then we also know that the mCV dt equal to the rho and the A, because we have the water tank, the diameter is 1 meter. So in here we have the 4 over pi d squared and the dH dt. So we merge all of the parameter we have in here. So that the the log forward pi d squared dt dh plus the log vj and the forward pi dj squared will equal to 0. So we cancel out all of the density, and we cancel out the forward pi in here. Okay, and we just reorganize our equations. So the d in here is the the d diameter in here is 1 meter. So here is the 1 meter dh dt is equal to the minus dj squared. So we have a 0.1 square. And the vj is the root of the 2gh. Okay. And so in that case here we just put the unknown parameter together, just move the h right hand side to the left hand side and the dt to the right hand side. Okay, so before that I use the calculator to compute all of the constant value in our equations. So the 2 times g root and multiply the 0.01. So in here it will equal to 0.0443 and root h. Okay, so in here we know that the dh divided the root h will equal to the 0.044 dt, 443 dt minus, and the minus. Okay, and we do the integrations both sides, and the time is start from 0 to tf, and the integration is 2 meter to 0.5 meter. Okay, so we can do the integration problems. So that will equal to 2 times h 2/1, and the interval is 2 meter to 0.5, and it will equal to the minus 0.0443, and the directly integrate the time is the tf. So that's equal to the 2 root 0.5 minus the 2 times root 2 will equal to the minus 2.2443 tf. Okay, so you can calculate the final tf answers. So I use my calculator to check the answer. The answer is correct or not, so I double check by my calculator. So it's equal to 1.92 seconds. Okay, 1.92 seconds. So it's quite close to the number showing here. It's depending on maybe the gravity, we use a different value in here. So so these questions we will involve the integration ideas, and so but the final answer we need to require here is how long. So you do the integration and then you can find out the final time point. Okay, so today we have a script, so I spend